Welcome back to DeepVisus, where vision meets depth. I'm your host, and today we're delving even deeper into the principles of intelligent systems, exploring how intelligent agents learn and thrive in the real world. Our journey today takes us through chapters 12 and 13 from part 4 of Understanding Intelligence by Rolf Pfeifer and Scheier. Last time, we laid out the foundational design principles for autonomous agents, emphasizing the power of parallel, loosely coupled processes. But even with a robust architecture, how does an agent truly make sense of the messy, unpredictable world around it? How does it learn to categorize objects or navigate efficiently without being explicitly programmed for every single possibility? This leads us to our central question for today. How does an agent's active engagement with its environment simplify complex learning challenges and enable truly robust and efficient intelligence? Chapter 12 introduces us to a cornerstone of embodied cognitive science, the principle of sensor-motor coordination. This principle fundamentally shifts our understanding of cognitive processes like perception, categorization, and memory. Traditionally, these were seen as passive information processing tasks. You receive sensory input, process it internally, and then act. Think of a classic object recognition system that tries to match a camera image to a stored internal template. This often runs into the object constancy problem. The same object can look vastly different depending on viewing angle, lighting, or background, making it incredibly hard to categorize. In fact, the book describes experiments where even simple categorization tasks, like distinguishing walls from cylinders using raw sensor data, failed miserably for traditional neural networks. These are what the authors call Type 2 problems, datasets where the mapping from input to output simply cannot be learned directly. But the principle of sensor-motor coordination offers a radical alternative. Drawing inspiration from thinkers like John Dewey and J.J. Gibson, it argues that movement is primary and sensation is secondary. Perception isn't passive reception. It's an active process. An agent doesn't just passively receive sensory data. It actively generates and structures its own input through its actions. Imagine a human infant exploring an object. They don't just stare at it. They pick it up, turn it over, put it in their mouth. They are actively manipulating their sensory input. This active engagement helps them to normalize the object's appearance and generate consistent sensory patterns, or invariances. These invariances simplify the learning problem, effectively transforming those Type 2 problems into Type 1 problems, datasets where the mapping can be learned. For example, the book describes an agent that learns about objects by simply circling them. This seemingly simple action generates correlated sensory data that allows the agent to learn object categories without complex internal representations. So, sensor-motor coordination is not just about moving, it's about moving to learn and to perceive. Building on this, Chapter 13 introduces 3 interconnected principles that guide the design of efficient and robust intelligent systems: the principle of cheap design, the redundancy principle, and the principle of ecological balance. These principles are all about leveraging the physical world and the agent's embodiment to simplify design and enhance performance. First, the principle of cheap design. Cheap here doesn't mean low quality. It means parsimonious and efficient. This principle encourages designers to 1. Exploit the physics of system-environment interaction. For example, insect leg coordination doesn't need a central brain. The physical forces between legs as they move on the ground help coordinate their movements. 2. Exploit ecological niche constraints. If a robot operates only on flat office floors, its vision system can be much simpler, as it can assume objects are on a flat plane. 3. Design parsimoniously, use the simplest possible mechanisms. Think of a cricket's matched filter that only registers specific sound frequencies, ignoring all others, rather than analyzing a full spectrum. This is a very cheap and effective design. Second, the redundancy principle. This states that an agent's design should incorporate redundancy, particularly in its sensory systems. This means having overlapping information from different sensory channels. For example, a robot might have both collision sensors and proximity sensors. When it bumps into something, both types of sensors activate, providing correlated information. This redundancy is not just for robustness, though it helps with that. It's crucial for learning. These overlapping, correlated signals provide the good data that learning algorithms need to extract meaningful patterns and generate behavioral diversity. Third, the principle of ecological balance. This principle asserts that the complexity of an agent, its sensors, motors, and internal mechanisms, must match the complexity of its task environment. You wouldn't give a simple gripper to a robot that needs to perform delicate surgery, nor would you give a human-level vision system to a robot operating in a perfectly controlled, simple environment. This principle guides designers to ensure that the agent is appropriately equipped for its specific niche. Natural systems, having survived evolution, are by definition ecologically balanced. So, to answer our guiding question, an agent's active engagement with its environment through sensory-motor coordination is key to simplifying complex learning. This active process allows the agent to structure its own sensory input, generating the invariances it needs to learn. Furthermore, by adhering to principles of cheap design, redundancy, and ecological balance, we can build agents that efficiently exploit the physics and constraints of their environment, leading to robust, adaptive, and truly intelligent behavior that emerges from the interaction of simple mechanisms with the world. And with that, we've taken another significant step in understanding the blueprint of behavior. Join us next time on DeepVisus, where we'll continue our fascinating journey into the principles of intelligent systems, exploring the crucial role of value systems and delving into a compelling case study on human memory from the perspective of embodied cognitive science. You won't want to miss it.